STEM fans, are you ready? Let's hear it for the world-class NASA STEM Stars team. From NASA centers across the country, we present Michael Logan. Hello and welcome to NASA STEM Stars, where students connect firsthand with NASA scientists, engineers, and innovators to learn about NASA missions, career paths, and opportunities. So today's topic is about UAS, or Unmanned Aerial Systems, commonly referred to as drones. I'm your host, David Alexander, from the Armstrong Flight Research Center at the Edwards Air Force Base, and joining us today is a very special guest, Michael Logan. He's an aerospace engineer from the Langley Research Center in Virginia. He's currently the acting associate director for research and development at the SWAV Lab. We welcome you to today's program, and thanks again for being here. Michael is actually going to share a bit about his background, career experiences, and the work he actually does for NASA, and specifically how he leads the charge for building and testing UAS. As you're listening to him share his story, we want for you to come up with some questions to ask him. So about half of our time today is going to be devoted to answering your questions. So please enter those questions in the chat throughout the conversation today, and we'll actually try to answer them all before we wrap up for the day. With that said, I'll turn it over to you, Michael, and his furry office assistant to get us started.
Yeah. This is Rosie. She's my furry office assistant.
Hi, Rosie.
Say hi, Rosie. There you go. You see, it's the social distancing thing down yet, so you know.
What an amazing little dog there. That's very terrific. Okay, so how about this? Why don't you talk a little bit about your background?
Sure. I'm actually an aerospace engineer, and I graduated from the University of Texas at Arlington. I'm actually a registered professional aerospace engineer. Written a lot of papers, probably like a lot of the students that are listening to this. Trust me, you don't stop writing papers when you get out of school. I'm also a lifelong learning advocate. I try and learn at least one new thing every day. And so I've learned a lot of stuff.
That is terrific. Why don't you talk a little bit more about how you actually got to NASA?
Sure. When I was a kid, I used to take foam egg carton tops and I'd cut out and make little gliders out of the foam egg carton tops. And so that kind of got me interested in airplanes. And a lot of what I did was learn how to make them better by trial and error. And, really got me interested in all kinds of aircraft, manned aircraft. I went and flew in a small airplane and that kind of stuff. So it was great. And I really wanted to learn, how do I do this for real? So I went to school, learned how to do that for real, got a degree in aerospace engineering, graduated, went to work for a defense contractor, and an opportunity at NASA came up. So I jumped at that, and I've been there ever since.
All right, great. That's a very interesting career path to NASA. Let's dive a little bit into what you do at the agency. Now, you currently lead the efforts for NASA's UAS, or Unmanned Aerial Systems. So what is UAS and why is it important?
Yes, unmanned aerial systems you can think of them as robotic aircraft. There are no people on board, and the vehicles will fly themselves. Sometimes they have help from a human operator, and sometimes they don't. Why this is important is because the amount of things that want to travel from point A to point B are dramatically increasing, and the need for things like inspections of bridges and precision agriculture, for example, where farmers can go and look at their crops from the air and determine specifically where to add water or fertilizer or whatnot. Those kinds of things really have the potential to create a much better world in the future.
Okay. And how big are the actual UAS that you work on?
Well, for me, I work on the smaller UAS, but NASA as a whole has very large aircraft. I think the Kana that is out at Armstrong has a wingspan of about 66 feet, and the smaller platform that you see me working on in the center picture there, that has a wingspan of about 6 feet. And the vehicle that you see me flying in the right picture is about 12 inches wide. So they can vary from very small to very large.
Okay. Are there different types of UAS?
Sure, there are fixed wing UAS, which means that they're more like a conventional airplane where you have a wing, a body, and a tail. And then there are what's called multi-rotors, which is what a lot of people think of when they think of drones. These are like helicopters with multiple rotors.
Okay, totally understand that. So we talked a little bit more about UAS, and I definitely really appreciate that. What specific missions are you actually working on currently?
Well, there's several actually. We finished a mission for the Great Dismal Swamp, which was a fire spotting mission. You can see that platform up in the upper left corner. Upper right corner there was a backpackable small UAS, where the group that we were doing that for wanted a fairly high speed unit that they could just pull out of the backpack, push the button, and have it go fly. So that was an interesting challenge. Then in the lower left, you could see worked on a turbine-powered small UAS that was completely autonomous, would take off by itself, fly itself around, and come back and land by itself. So that was really interesting, and it would do that really, really fast because of the turbine.
How fast were those going?
The fastest I've seen it was 160 knots, which is about 180 miles an hour. So just under 200 miles an hour.
Wow, that's definitely amazing on this end. And in terms of the SWAV lab, do you work on any specific types of long durance type aircraft?
Sure. One of the things that we did as part of the lab was we were looking at, the Air Force came to us and said, hey, can you wrap an airplane around this fuel cell that they were developing, where the fuel cell would use camping fuel to generate electricity, and then that would power the electric airplane. So we actually had two different designs. The one in the lower left is a flying wing design that we put together, and then the middle on the top is a more conventional configuration where it had a kind of a boxy fuselage and a tail and a wing. And you can kind of see on the lower right picture how that kind of looks when the top is off and all that kind of stuff. And it's getting a CAT scan.
Okay, and so you definitely specialize in small UAS prototypes and things like that. Can you talk a little bit about some of those little aircraft that you worked on?
Sure. A lot of times a group will come to us and say, hey, can you design a vehicle that will do X? So we'll take out a sheet of paper and figure out how to do that, do some analysis and so forth. The project on your left was a competitor to the picture that you saw earlier. Again, a backpackable thing that was very small, compact, they could take out and go fly. The one in the center was actually for search and rescue, where the vehicle could take off vertically and then transition to forward flight to go, let's say, to the point of a partially collapsed building or something, and then go back to that vertical sort of hover and maneuver around inside the building, looking for people that need to be rescued.
Okay.
The platforms on the right, again, are things that we actually took from the Army that were target drones, and we converted them to be autonomous UAS.
Now, right now, we have a question here from a student, and it has to do with small vehicles such as the ones that you spoke about. How does the helicopter in Perseverance rover work in the Mars conditions? I'm asking this as this is an unmanned aircraft.
That's correct. As far as I know, I'm not involved with that particular project, but as far as I know, it is very difficult to fly a helicopter-like vehicle in those conditions because the density of the atmosphere on Mars is very, very low. You can compare that to, let's say, up at 100,000 foot altitude here on Earth. So it's very, very difficult to design a vehicle that will operate efficiently in those conditions. So, my hat's off to the folks that are actually doing that.
Absolutely. And I have another question here from a student, and maybe we can segue into the engineering design process here a little bit. But what do you think are some of the most important skills to become an aerospace engineer at NASA?
I would say the most important one is creative problem solving. Uh, if you know how to go through the process of problem solving, I think it doesn't really matter whether you become an aerospace engineer or some other kind of engineer. Those skills are very, very necessary for whatever kind of career path that you choose. So think about that. Obviously, the math and the science and that sort of thing are going to be common to a whole lot of different career choices. So I'd say that's probably creative problem solving is something to learn a lot about.
Exactly. I mean, what does it actually take to be able to implement a design from concept to flight?
We go through a process, right? The first thing we do is, you have to stop and think a minute. Okay, what do you want the vehicle to do? What problem are you trying to solve? What kind of payload do you want this vehicle to carry? How far do you want the vehicle to carry that payload? How long do you want it to stay there? How fast do you want it to get there? All those questions kind of have to be put together in a list, and those are called the requirements. Once you have the requirements for what you want the vehicle to do, then you can start looking at doing some analysis and use what are called computer-aided design programs or CAD programs to make a model of those vehicles. And once you have that, then you can take those and actually build the vehicle the way it was designed. Once you get done with that, then you transition to ground testing and you make sure that everything is kind of working the way it's supposed to and that sort of thing. And then finally, if all of those are successful, then you go fly. And that's the fun part.
Totally understand about that. Now, what is it going to take for these vehicles to actually fly over people?
Well, there's a couple of things. One is there needs to be some sort of mechanism or software or whatever to be able to control all these different vehicles going hither, thither, and yon, so that, kind of like the way we do with manned aircraft now. I need to know where you're going, and you need to know where I'm going, so that we don't cross our paths. But the other thing involves actually improving the safety of the vehicles themselves. And I think we have something that we can talk about here shortly.
Yeah. I actually have a question here from a student. What are the uses of UAS according to their types uh, that you've actually worked on? I mean, obviously, NASA has worked with numerous partners. Can you give us an example of some?
Sure, I'll give you a couple. For the fixed wing platforms, we used those in working with the Great Dismal Swamp fire spotting mission, where they had a problem with if a fire occurs, like after a lightning strike, thunderstorm kind of thing. If they don't catch the fire in its earliest stages, it can burn out of control, right? So you need to catch those fires when they're really small and kind of nascent. So what we did was we put two different cameras on a fixed wing platform, and we flew that around. We had a color daylight camera that would help you to see smoke and that sort of thing. And then we had an infrared camera that would look at and find hotspots. So we would deliver that video down to a ground station, and the fire captain at the Great Dismal Swamp was watching that and could figure out where to send his folks and that sort of thing. We also did some work with a multicopter that you see there in the upper right picture, and that was a similar sort of thing where once you thought you saw something, you could send that directly to it and have it hover there and stare for a while, sending video back to you.
Wow, that is definitely truly amazing on this end. I mean, it makes the little drone I have look like peanuts compared to what you've been working on. I have a really cool question here from a student, very groundbreaking. It says, what are the future applications of UAS? So, what is the future of UAS?
Well, so there's a lot of things, right? Pretty much, and I got to say, we don't know all the applications of UAS, right? Somebody is going to come up with one that we haven't thought of yet. But we know there are things like package delivery. There are things like transporting human organs for transplants and things like that back and forth to hospitals much, much faster than they could before. We're already seeing folks in underdeveloped countries use these platforms for medicine delivery. So, there's that kind of thing. There's all manner of infrastructure inspection, like, buildings and bridges and roads and things like that. There's all kinds of agricultural kinds of applications for that. So there's a lot of different applications for that. The future comes in, I guess you could look at it as we need to kind of look at how we handle that traffic, particularly at low altitudes. So hopefully that answers the question.
Yeah, definitely. And I think we have some footage here. Maybe we can take a look at one of the projects that you worked on with respect to AAM, or Advanced Air Mobility.
Sure. If you think about it, we worked on a project called UAS traffic management, which was kind of the first attempt at developing an automated system that would act kind of like a traffic cop, right, or kind of like the way the current manned aircraft traffic management works, but without the humans involved, right? So we partnered with the Lone Star UAS Test Center, where I'm at currently, and they did a number of small UAS operations in downtown Corpus Christi. And you can see some of those drones on the video. That particular one that just took off was mine. So, and they were able to go and get video pictures, and they were able to test out the system, and also test out various procedures, if you will, for avoiding each other, right? Where there are multiple drones in close proximity, but the UTM system knew about that and could keep them separated so they didn't run into each other.
Okay.
That technology migrates into what we call urban air mobility, which is a lot broader than just small drones. And from there we go to advanced air mobility, where you introduce things like automated air taxis, for example.
Did you have to run a simulation, for example? One of the students was very curious about simulations. Are you able to fly a newly designed UAS in a simulation before testing it in the atmosphere?
Oh, absolutely. Yeah. And in fact, a lot of the work that was done under the UTM project was done in simulation before we actually took it out and flew it in real life, in downtown. So that worked out pretty well. There's also a number of simulations where it does its own aerodynamic analysis, for example, and it uses what it computes terms of those aerodynamics to feed into the simulation. So you can see, oh, you know what, this concept doesn't have quite enough lift where I need it to be, or this one's really hard to control, or whatever. So yeah, we do a lot of simulation before we actually go fly.
Okay. Um, just another question here on this end. What do you like about working at NASA? What's very unique about working at the agency?
Well, for me, I get challenged a lot, right? Uh, Here's a problem that nobody knows how to solve. Uh, Take a shot at solving it. So for me, there's, the challenge is actually overcoming these problems or developing a technology that will, help enable something to happen in the future. But the other big thing is I get to work with students, right? I've worked with all kinds of students. The picture you see there on the left were a couple of at-risk high schoolers that I worked with in my lab, and I put them to work. They actually built a vehicle, and I told them, okay, you're going to have to be real careful as you build this vehicle, because guess what? You're going to have to fly it. So, it made them a little nervous, but they got the point. But there's also, design teams that go through the design process that we were talking about earlier, like the picture you see there in the center. They custom designed a vehicle for the Great Dismal Swamp fire spotting mission. And then you see up in the upper right picture, groups of students who are hands-on, learning how to actually, make things out of composites.
Okay, very good. Well, we're very happy to hear that you love students. A couple students needed a few tips on some career advice. Maybe you can answer these questions, and we'll segue and talk about careers for a moment. Student asked, I want to be an astronomer, and how could I engage in that type of opportunity? Please advise.
Well, obviously, if you're interested in astronomy, then you're going to start looking at stars and things like that. And generally speaking, there's some kind of observatory nearby. And so what you'd want to do is you would start going to those observatories and either taking a tour or getting to meet the people there and that sort of thing. And as you get more knowledge and that sort of thing, then you can go on and go to college and get your degree, and start working in those kinds of areas, because by then you'll already have a good understanding of what it is, how it works, and the techniques and that sort of thing. So that's what I'd suggest.
Okay. Another student had a specific question here. What is the main difference between aerospace engineering and astrophysics?
Well, typically, aerospace engineering looks at air vehicles in the atmosphere here on Earth, whereas astrophysics typically looks at the movement of planets and how they interact with each other and that sort of thing. So that's kind of, in a nutshell, the difference between the two.
Okay, great. And another question here from a student. Um, what are some of the main things that you need to know or learn in order to do your particular job?
Interestingly enough, there were two things that I had some college students come into my lab, and they didn't know two basic things that for hands-on work was really important. One is how to read a ruler, and the other is how to solder wires together. Other than that, if you have the basics of math, you have the basics of physics, you kind of have an understanding of how airplanes work. Uh, if you go to college and get that degree, then you'll have a fundamental understanding of that. The other thing is mechanical things, right? Uh, if you have a basic understanding of how stuff works, and I think there's actually a website out there called How Stuff Works. It's good to know that sort of thing, right? It's also good to, particularly when you're a young person, to try different things. I'm going to take this apart and see how it works. Right? Be sure you put it back together before your parents get home. But anyway, you do that sort of thing, right? That's how you learn.
Yeah, absolutely. Another career question here. What are some of the problems that are faced by aerospace engineers while flying aircrafts, which are remotely controlled and unmanned? And does your heart break when you crash a UAS?
Yes and no, right? Part of hard part is if you are trying to fly it the way you would fly a model aircraft, that's easy enough to do when it's close to you. When you send it out a long distance, then it becomes a lot more difficult, right? It becomes more difficult to see, more difficult to figure out which way the thing is pointing, and so forth. So that's a little bit of a problem. Uh, but the autopilots now are smart enough to be able to bring that back to you. So even the open source Pixhawk type autopilots will bring it back to you. As far as crashing, I haven't crashed all that many, but the main thing to do is when you have a crash is figure out why it happened and try and figure out how to keep from that particular problem from cropping up again. So we always look at it as a learning experience. And typically, if you put something in the dirt, as long as it doesn't hurt anybody, you've got a pile of parts and, now you've got something you need to go learn about. So learning opportunity, lifelong learning thing.
Very good. Thank you for those explanations. Looks like we're just about out of time for today. But before we go, we have a student challenge for our students online today. As you've learned today, NASA is leading the nation to quickly open up a new era in air travel called Advanced Air Mobility, or AAM. And the vision of AAM is that of a safe air transportation system for passengers and cargo capable of serving previously hard to reach urban and rural locations. So, in this activity, you will actually design an air taxi, create a model of it, and share it with us on social media using the hashtag NextGenSTEM. So, you can see the link there to the activity in the chat box, and that will actually take you to the website so you can begin completing your design. Now, two more things before we wrap up on this end. I want to say a special thank you to Michael for coming on our show today. It was very awesome to get the opportunity to be able to speak with you and especially learn more about the cool work you do at NASA. Lastly, join us for our next STEM Stars chat on August 6th at 3 p.m. Eastern, where we're actually going to learn more about the intern experience by students working with scientists as well as engineers on the James Webb Telescope. So thank you everybody for attending today's program. We really appreciate it. We will see you next time here on NASA STEM Stars. Take care, be safe, and have a great day. Till next time.
Thanks.
Thank you.